I'm delighted to be here, though the challenge I was given of trying to do something that would sort of introduce the challenges that we face in aerosol measurement is a little bit daunting, especially when I read the range of topics that are being presented here. I came here from a field project that we have going in Monterey. We went there to measure clouds. We've had no clouds in the last week and a half that we've been flying, but we found some fascinating aerosols over the red tide, which is an immense area right now. So we're now looking at biological particles when we went out to look at clouds. This is one of the key features of aerosols is you never know what you're going to find, especially when you're doing ambient measurements. You go out to measure one thing and you discover you need the tools to measure things very different than what you had planned. Now, if I can figure out which is the right switch there. The question of what is the ideal measurement is one that has been raised by a number of researchers over the years. Kjell Friedlander wrote a very nice paper on this in 1970. Peter McMurray updated it considerably in 2000, trying to look at what it is that we want to measure, what do we measure now, and where do we need to go. And I'd like to look at that, use that as a perspective to think about what we're doing here. So we could start out with the integral measurements. So one of these should be a pointer. Oh, that wasn't it. Oh well. The top, we see the integral measurements. Total numbers, condensation nuclei, cloud condensation nuclei, total mass concentrations, and on and on. PM 2.5, very limited resolution, fall into that category. Then we go to moderate resolution, where but those first measurements, some of them we can measure with very high time resolution. We go to the early measurements where we could do size segregation, cascade impactors. We could get modest size resolution, but it would take hours to days to get information. And with analysis, we could get some substantial composition information. Then we have moved on towards higher and higher resolution in size. Many of our measurements now, we're able to acquire data that tells us quite a bit about the aerosol on timescales of minutes. We have other measurements, filter measurements, the composition measurements, ultimately the mass spectrometry measurements. Yes, I have one in my bag, thanks to you. But with the mass spectrometer, we can get composition information at different degrees. We don't get chemical composition, but we get good indicators of the composition. We're not gently determining the individual molecules. We're getting fragments from them, and we have a complex soup that we're trying to diagnose, to analyze. But we can get very useful information, and this is providing us with tremendous insights into the nature of the aerosol. I'll bias this a bit by some of the instruments I've worked a lot on, but I'm going to bring in quite a few different instruments and methods, and especially to look at a wide range of contributions. The DMA is one of our primary tools for characterizing fine particles. It gives us a physical size distribution. It doesn't give us directly any chemical information. Key feature of the DMA is that we're separating particles according to their migration velocity, which scales with the diffusivity. The performance of the DMA at high voltages, we can get very high resolution out of it. We can characterize this in terms of a Peclet number for migration, which is the electrophoretic migration over diffusive transport, which ultimately comes down to EV over KT, the electrostatic potential energy of the particle in the instrument over the thermal energy times some geometry function, and if we have multiple charging, the number of charges. So this is one of our very powerful tools, but this alone does not give us data. we need to bring other parts into it. This one got scrambled quite a bit, but we have a variety of different DMAs from the original Knudsen and Whitby design. Was not the original DMA. The original DMA was by Ericsson, published in 1918. It is actually an old technique. He was using it to measure molecular ions. We are back to using the DMA now for measuring molecular ions, led in large part by the work of George Reichel, who really started us off in a new era of developing new instruments, higher resolution instruments. Juan de la Mora, who has for, is that 2 decades now, been continuously advancing the state of the art. He produces the instruments that are really the gold standards in terms of the ultimate resolving power of the instruments. There are some other designs that have come into play. We've built radial flow designs that have allowed us to make instruments that are better suited for small particles. There were some other people who built radial designs trying to measure big particles, but that's not so practical. We've ultimately taken this down to a very small instrument, one that you see is small enough to sit in a coffee cup, that actually will take us down to 1 nanometer. And with the current versions, with a resolving power of about 15 down to 1 nanometer in size. We can go very small. The characteristic that we use to describe how good a job these instruments do for sizing is adapted from mass spectrometry and other spectroscopies. It's the resolving power or resolution of the instrument, which we characterize in terms of the mobility. That is, the mobility at which particles are transmitted with the highest efficiency over the full width of half of that maximum transmission efficiency. So we use this as a metric to characterize the DMA. And if we look at the DMA, as we go out to high voltage, where migration dominates over diffusion, the resolving power is determined by the ratio of the aerosol flow rate to the sheath flow rate. That's this beta. The inverse of that is the asymptotic resolving power. As we go down to low voltage, the resolving power scales as the voltage to the 1/2 power. The upper bound voltage we can go to is determined by electrostatic breakdown in the atmosphere within the instrument, taking into account the geometry of the electrodes. Typically, we can work at about 10 kilovolts per centimeter with a typical gap of 1 centimeter. That takes us to a limit of about 10 kilovolts, which means that diffusion becomes important as you're getting to the ultimate resolving power by the time you go out to an asymptotic resolving power of 100. So we go down, if we're willing to accept lower resolution, we can go down to lower voltages. But there's a limited dynamic range, and that dynamic range that we can probe by changing the voltage alone diminishes as we go up to very high resolving power. Nonetheless, DMAs can resolve down to about 1% on mobility, which is a tremendous capability when you start trying to bridge the gap between the molecular measurements with mass spectrometry and the mobility analysis instruments. We've recently introduced a new analyzer, which is an opposed migration analyzer. We have 2 porous electrodes. We introduce the aerosol filling the gap between the electrodes and apply an electric field that causes the particles to migrate against the counterflow. So there's a slow drift towards the exit port, but migration is countered by the crossflow directly. Here we change the scaling for diffusion. In the DMA, the aerosol fills only a very tiny fraction of this space between the electrodes, so it's the width of that region of aerosol that determines when diffusion is important. Here, the gap between the electrodes determines when diffusion is important. This is a very important result because it's going to allow us to do some very fine separations. This is something that I received in the mail just yesterday from one of my students doing a design of a new version of this instrument for a particular application, showing what happens as you sweep through sizes of particles going through one of these classifiers. And they go from particles being lost to the upper electrode to particles being lost to the lower electrode as we continuously scan. When we look at the resolving power, the DMA, if we look at asymptotic resolving power of 10, we start seeing considerable effective diffusion at about 20 to 30 volts. With that change in the scaling for the OMAC, as we go down to 1 volt, we see that effective diffusion. Now with the OMAC, we start seeing much larger losses at the same point where we see diffusion, whereas with the DMA, we're not losing as many particles. So the DMA can probe way down into this diffusive region. The OMAC, we really can't go there. But we can ultimately get a wider dynamic range at moderate resolution, or theoretically, we can go to very high resolution. To date, we've built instruments that have a resolving power of about 25 down to 1 nanometer. So we've got a classifier. We still need to count the particles. The standard tool is the condensation particle counter, which I think most of you know about. We saturate an aerosol sample with vapor. We cool it to produce supersaturation, condensing vapor on the particles, grow them up to a size that we can count them optically. Very, very simple concept. The introduction of the continuous flow CPC allowed the use of the DMA to make size distribution measurements. It allowed us to introduce a scanning technique which makes measurements really quite rapid. But the scan rate is limited. It's limited by the detector. This big volume in the detector acts as a mixed reactor, as a stirred reactor, has a very slow response time. Here are response times for different commercial CPCs. And we see response times out to 1 to 10 seconds. So for each measurement, the companies may tell you you can make a measurement in 1/10 of a second. And yes, you can count particles for 1/10 of a second, but you're integrating over a second or 10 seconds with that same instrument. So you have to be very careful in interpreting the measurements. This limits the rate at which we can do size distribution measurements. There are, and PowerPoint did its wonder again. We have here a couple of advances that have been very important. Peter McMurray introduced 20 years ago, 20 plus years ago, the ultrafine CPC, which reduced the diffusional losses. It, at the same time, reduced the response time by an order of magnitude. It made it a much faster instrument. But it has a very tiny flow volume. So the counting statistics, while they're great when you use it just as a CPC, if you use it as a detector for a DMA, they're pretty bad. It's not a very good detector for a DMA. It's a fantastic CPC on its own. The recently introduced water CPC by Suzanne Herring also gives a relatively low response time. Doesn't go down to quite the 2.5 nanometer threshold, but it has a higher aerosol flow rate. This is actually a very good detector for use with the DMA. We can go to other techniques to get fast response. If you simply use an impinging jet reactor to rapidly mix, and I pulled this off yesterday in response to, here is the mixing zone. You have a very tiny mixing zone in which you use impinging gas jets to induce intense turbulence, homogenizing a hot vapor with a cold aerosol to produce supersaturation on a time scale that's very responsive. Response time of this, and that should be milliseconds, 10 milliseconds response time. With this, one can do size distribution measurements in as little as 5 seconds. And they've actually gone down to 1 second full scan size distribution measurements. Of course, counting statistics become an issue as you go there. So we have some powerful techniques, but what are we going to do with them? If we look in the atmosphere, this classic picture from Boyan-Komala shows what's called a nucleation banana. We have a background aerosol out here at 10 to 100 nanometers overnight. As the inversion lifts, that mixes out and dilutes, providing the conditions that allow a nucleation event to occur. And when plotted on this logarithmic scale, you get this curved profile that has been labeled the nucleation banana. It's an incredibly powerful technique or observation. This was done with stepping mode DMA measurements, and it was long thought that nucleation was an unlikely event in the open atmosphere. We now know it occurs just about every place anyone has looked. In fact, when you take the data that has been developed on nucleation in the atmosphere and look at a global scale, you find the difference in particle formation with boundary layer nucleation or without is quite substantial on a global scale. We're not going to see this with CPCs and DMAs. We can't do in situ measurements over the entire atmosphere. We're going to have to bring into play the remote sensing community to help us to understand the phenomenon at this scale, and the modeling communities both. There's a new experiment, CLOUD, that is one of the cleanest, or is the cleanest chamber yet built, that allows us to simulate these nucleation events with great precision and control. We can reproduce them repeatedly in the laboratory, and we can use this now to begin to understand the fundamentals. So we're now using these tools to look for the fundamental events. But to do that, we need better detectors. So Peter McMurray came to the rescue once again. His student Iida examined 800 different organic molecules as possible working fluids for the CPC and selected a candidate, diethylene glycol, that they could use to activate particles and grow them up to a few tens of nanometers in size. And grown up to that size, you can then use a conventional CPC to grow them up to detectable size. Now that's putting two CPCs in series. It becomes a slow response instrument, but it can detect particles down to 1 nanometer. And this has been done in a number of different modes. Originally done with the TSI ultrafine CPC, but it's also been done with the mixing type CPCs in something that's been labeled the particle size magnifier by the Helsinki group. Going with diethylene glycol, we do have to think a little bit about what it is we're using, what are the particles we're activating. Diethylene glycol tends to be more sensitive to composition of the particles than does butanol. And so, depending upon whether we're looking at positively charged particles or negatively charged particles, we see considerable variability in the activation. But we can use this as a tool, and we can not only use it as a counter by varying the supersaturation in the instrument, we can use it to get a Kelvin equivalent size, an activation equivalent size, and that's been used extensively to look at nucleation processes in the atmospheric aerosol. Then we try to look at the activation behavior, and the question comes, we see these nucleation bananas. Now here we see the background gas ions, we see one of these nucleation bananas occurring. We want to extract a nucleation rate from this. To do that, we need to, in some way, track characteristics as particles grow along this curve, taking into account all of the losses that are occurring in the process. We need to know not just the very tiny particles, we need to know the entire aerosol in order to map out the dynamics of these tiny particles and back out the nucleation kinetics. And this is scrambled beyond belief. I think I will leave this to Doug to talk about. So I'm sure he will have something on this. But let me go to one that I did not do all those errors came out of my using the crop feature within PowerPoint, and it apparently does not always work. This is the first time I've seen that performance, though. This is an experiment where we flew the Romiac. We used diethylene glycol in an ultrafine CPC pushed to the limit in the way that Kwong, Wang, and McMurray demonstrated to take its threshold down to about 1.3 nanometers. Here we were flying the instrument. We're probing an unusual source. All this stuff in the background, that's the Harris Ranch. If any of you have ever driven I-5 in California, you go past one area where you hold your nose. This is it. It's one of the biggest cattle feedlots in the US. It's an incredible amine source. And here we're seeing a nucleation in the plume as we go downwind. This is estimated, this is flight time, but it says we go downwind from that source. Ultimately, we get to the question of what is the ideal instrument. And the ideal, as Peter and Sheldon both suggested, was continuous size measurements without any discretization, continuous time measurement, and perfect composition. Well, I would add phase, morphology, and then ask whether we could actually do the measurements. So an important question that we need to ask is, why do we want to or need to measure aerosols? We want to understand the atmosphere. Look at the aerosol yield in photochemical reactions. Understand atmospheric dynamics, climate change. Look at the health impacts. Do risk assessments. Look at disease propagations, the bioaerosols. We've been measuring toxic particles from the red tide. It's going to be very interesting to see what we get out of the aerosol mass spectrometer, because we should see some interesting new signatures in some of the species we're looking at. When we look at the reactor technologies that Pratim was talking about, we need to characterize aerosol products. And for those processes, we need to do processor quality control. There are many, many different reasons for measuring the aerosol. I'm going to take one and look at what we need to measure, because this raises a question. Most common measurement today for aerosols, at least for ambient aerosol exposures, is PM2.5, a measurement that was put in place to deal with the need to have a standard to which one could regulate. It's a surrogate for risk to human health. It's inhalable particles that can penetrate into the lower airways. Penetrate, not deposit. Doesn't measure anything about deposition. It measures the mass of particles smaller than about 2.5 microns. It misses part of the tail of the particles that do penetrate to the lower airways. It measures a lot of the residual aerosol from soil dust and the coarse mode particles. It's an imperfect measurement, but it's what we have as a standard, and as a result, it is the major kind of data that epidemiologists have today to look at health impacts. Is it the right measurement? Well, is mass even the right measurement? It may be for coarse particles. It's being questioned for fine particles. Mass, basically, it's looking at chemical toxicity. We look at number. If we have a huge number of particles, we can overwhelm the macrophage population. So instead of particles staying after deposition, staying in the lower airways for a few days to weeks, they could stay for months because there are just too many of them for the macrophages to clear out. Surface area. How readily can material be leached from the particles? These are all suggested as possible metrics for health impact. The PM2.5, it measures mass. How good does it job of measuring risk? If these are the appropriate measures, well, we've been taking a look at that. So we're looking at the question of what particles would deposit in the head and neck airways, in the tracheobronchial region, in the bronchiolar region, in the pulmonary and alveolar region, in the different compartments of the respiratory tract. We use standard lung deposition models to look at that. Now, to take a test case, we've taken an air pollution episode. We took one of the most polluted cities in the world, New Delhi. This is some data looking at fine particles from New Delhi from Munkanen et al. This is a simulation of that same data. We've used this simulation. Why do we use a simulation? Well, this is biased. It's biased by the fact that the measurements don't capture everything. So here we're modeling the whole aerosol. We don't have any instrumental biases in the data. What we're going to do is use this data to challenge computationally, in silico, as the biologists say. We're going to challenge the instruments, challenge the respiratory tract, look at what we see with different measurements. So what we'll do is we'll take a size distribution, our input, at an instant of time. We'll simulate a measurement. Given that measurement, we'll invert the data, having put in noise, having truncated the measurements just as the instruments do, come up with an estimated size distribution measurements as best we can do from the data allowed, estimate the dose to the different regions of the respiratory tract. And we'll compare that to what we would get if we directly calculated the dose based on that same measurement. So this is an apples comparison rather than introducing unnecessary biases. And this is the bottom line. What I plotted here is measurements comparing PM2.5 or the number smaller than 100 nanometers with a perfect DMA measurement. So let's start here with mass and PM2.5. The color denotes time. So we start out here and we see over time we're following what looks like a pretty straight mass number. Now there's a difference in factor that we're getting out from the numbers due to truncation and other biases within the measurements. This is taking the best information that we would normally use in doing the inversion. We need to be able to do a better job, and this is pointing out places where we need to look more closely. That's number. If we look at surface area, we go here, down here, and up here. It's following relatively similar trend, but it's not quite as good. If we go to number, we go down here, up here, down here, doesn't look at all like a strong correlation. The number in no way is correlated to the PM. Not a surprise, but something that we need to pay attention to. If we say number is our measure, and we took a CPC and did a total number measurement and compared that with the number we would get by integrating. If we look at mass, no correlation. If we look at number, we see a fair amount of scatter. Why? Well, our, quote, perfect measurement actually has real instrument characteristics in it. That is, the measurement doesn't cover from 0 diameter to infinite diameter. There is truncation in it, and those truncation errors lead to uncertainties. This is just one example. We cannot afford to put DMAs, at least as they're currently built and marketed and priced, we can't afford to put enough of them out into the area to look at some of the spatial variations in air quality that are important for health effects. There are gradients in asthma along the 710 freeway in Los Angeles, where in a distance of 300 meters, the asthma incidence drops by a factor of 2. As you go from the freeway out, it drops dramatically. This is thought to be a particle effect. We don't have the data today to say anything quantitative about that. The epidemiologists cannot make the case based upon the data. We need instruments that we can put out there that can be out there every day for years And the most important thing for the epidemiologist is not that we get data to the highest size resolution or the highest concentration resolution. It's that we get data every single day, that we not miss a datum. When we look at the bias that we get out of the measurements, we say, suppose we took our DMA and we made it simpler. And in fact, I'm going to throw the DMA away. The OMAC is easier to make. We can make it cheaper. Let's sacrifice resolution. If we take the classical DMA, we're operating at a resolving power of 10. And compared to our ideal measurement for that same scenario that we looked at, we have biases that are within 1% or 2. As we drop the resolving power, we see during that nucleation event, we see a bias that might be 30%. 30% is small potatoes when you're starting to talk about the statistics of human health. There are so many variabilities that we need to take into account in terms of the exposure that we can tolerate this kind of degradation. We don't want to go down to a resolving power of 1, becomes pretty uncertain, and the biases become quite oscillatory down here. But we could probably work at a resolving power of 2 or 3 and do a very good job of providing dose to respiratory compartments. And on that basis, we could start giving them data that the epidemiologists can use for looking at health. I'm not the person who's going to address the health question, but I could see the need for the data. And so I've been looking at the question, how we can generate the data that we need. So, in conclusion, aerosol systems are complex. And we can't get away with a single measurement. We need the mass spectrometers. We need the Apitoff to get down to the smallest molecular clusters. We need all of the chemical tools that we can bring to bear. We need remote sensing to bring in the large scales. We need ability to look at biological particles. We need this entire community thinking about the measurements and bringing different tools together to try to solve some very complex problems. If we just thinking about the nucleation problem, to understand nucleation in nanoparticles, we must know about the large particles that are there because they become tremendous sinks for the nanoparticles and change their dynamics completely. Perfection in our measurement scenario, it's in the eye of the beholder. It depends upon what you're going to do with the data. The highest resolution is invaluable for fundamental studies. We need it to look at nucleation processes to really understand them. We need instruments that go beyond any that we have today. For the mobility instruments, we need the composition measurements. We need to push the mass spectrometers out beyond 2 kilodaltons so we can get larger regions of overlap with the more physical characterizations that we have in the aerosol measurements. To look at the fundamentals, we need single particle experiments that actually probe what's happening in a single particle. That eliminates the variability from dispersion in particle size and particle composition. The time and space resolution in measurements may be equally important. Sometimes we'll need large numbers of measurements rather than the greatest possible precision. And if we look at the small UAVs that are being developed today, an ability to deploy instruments on those to go probe local sources. What could we have done at Fukushima if we had some instruments that could detect the air ions efficiently in a tiny platform that could find and track the plumes? Would have been immensely valuable. There's still a lot of room for improvement, and I'm hoping that this couple of days will bring some of that to light. And with that, I'll conclude.
Well, in spite of PowerPoint not cooperating, that was a fabulous stuff. Okay. We have probably time for one question.
let's use the microphone because there's several people online.
Okay, so it's a very comprehensive talk regarding aerosol measurement technology. I just got a very fundamental question here. I mean, like when you do the DMA measurements, I mean, like you talk a little bit about bias, you know, in terms of resolution. And my question here is, what is a bias in terms of chemical composition? I mean, like, you know, like a DMA, I mean, like particularly when you're measuring nanoparticles, you have a few nanometer particles that may eventually, I mean, may as small as like molecular clusters. And some of those may made like come from acid-base reaction, like sulfuric acid means it's very, very stable, where others may actually be very weakly bonded complex. I mean, these like organic, oxidized organic sulfuric acid. So what is your view? I mean, how to resolve those kind of like the bias in nanoparticle measurements? Yeah, I mean, like with the mobility approach, and just give me some, your take on this.
Great question, Pandora's box. First, I did not mention the charging problem. The charging theory everyone uses for inverting DMA data is wrong. It's not good for big particles and it's not good for small particles. From about 20 nanometers to 100, it's pretty good. Maybe 200. As we go down to the very small particles, we have to start thinking about the physical chemistry of the charge transfer reactions. The charging of the particles, the kinetics have to become important as we get down to small size. Exactly where that occurs, Juan may be able to say something about that because he's been looking at some of these things, but we really don't have the data right now. So there may be a bias that occurs in the charging. There's another bias associated with composition that I did not mention, which is the volatility of the particles. Almost all of our aerosol instruments cook the particles before they measure them. We've got all the electronics packed into a box with the sensing technology. All those electronics are heating things up. When we go to a CPC, we've got major heat sources. We may be evaporating the particles before we measure them. And that's introducing another composition bias. The stability of the particles in the measurement process is an unaddressed question. I wouldn't say it's an unanswered question. I'd say it's really an unaddressed question. And it's one we need to begin thinking about. I think it's a critical issue. Beyond that, there may be other chemical effects that we need. But the interaction of the chemistry with things like the mobility measurements is something we need to look at. And we need to look at chemically based sensing detectors for the mobility analysis measurements. Now that's a real challenge because only a tiny fraction of the particles are actually charged. But ultimately that would help answer your question, but we're not there yet. Maybe somebody here has an idea.
I think we have only time for one question here, so let us thank the speaker again. Thank you, Rick.